Hello students. So in the last class we have discussed about what the uniform circular motion, and we have derived a certain relationships which are like this one is in general true for all sorts of motion. And then we had derived what the acceleration in the case of uniform circular motion, that is only true for what for the uniform circular motion, not it is in general true. Okay, not in general. So now guys, today we are going to see uh, the relationships that we have to develop for accelerated circular motion, and these relationships are going to be more general compared to the derivations that we have discussed in the case of what uniform circular motion guys. Okay, so let me show you few things guys. So see, suppose guys, this is your circle. Okay, this is your circle, and this is the center, and there is the particle which is moving. Okay, so guys, what is accelerated circular motion? Accelerated circular motions means what guys? Here the meaning of accelerated circular motion is that dv by dt of mod of v, of course, d of mod v by dt is not equal to 0. It means what guys? It means its speed is changing. Its speed is what? Changing. And of course, if its speed is changing, it means what? The distance that it is going to cover in the same time interval is going to be different. And of course, if it is going to cover the different distance in the different time interval, then of course guys, it is going to cover what? The different angles also what? In the different in the same time interval. It means what guys? That d omega by dt is also not equal to 0 in the case of what is? In the case of accelerated circular motion. That is the meaning. Okay, now if you see guys, suppose here the velocity is v, and let's say here when you reaches, the velocity becomes what? V dash. Okay, velocity becomes what guys? V dash. It means that there is some a tangential guys, some a tangential is acting on the body. Okay, there is some a tangential is present there, which is what guys? Is changing the speed. Okay, so of course a tangential is non-zero now guys. Okay, a tangential is non-zero, and of course if particle is moving on a circle guys, you are going to have what? A centripetal for sure. Okay, you are going to have a centripetal for sure. It means guys what? Now you are going to have two different accelerations, and which are non-zero, which are guys what? Non-zero, which are what guys? Which are a, if I write, which is the total acceleration, it is going to be equal to what guys? A tangential plus what? A centripetal. Okay, there are two accelerations which are going to come. One is what guys? A tangential, and one is what guys? A centripetal. And of course guys, this A should come by the differentiation of what? dv by dt. That is equal to what guys? A tangential plus A centripetal. Okay, so when we will solve this problem, we should get guys what? One, this component which should be what guys? Which should be tangent to the path. Okay, and there should be one which should be what guys? Towards the center. Okay, so I'm going to derive these two by the general relationship that we have developed for the velocity guys. Okay, so if you see guys, if you see, the v vector is equal to what guys? Omega cross r. Okay, is equal to what guys? Omega cross r. So here guys, here if I differentiate this, so guys, what I will write? I will write dv by dt, which is your total acceleration, and that is equal to what guys? D omega by dt cross r plus what guys? Omega cross dr by dt. Okay, so that would be the guys, the general derivation. Now guys, here if you see, the d omega by dt is not going to be 0. It is going to be what guys? It is going to be non-zero. And guys, see, as we have given the name of rate of change of velocity as a acceleration. Here guys, rate of change of angular velocity, we are going to give a different name, which is known as guys what, angular acceleration. So the rate of change of angular velocity will be known as what guys, angular acceleration. So let me put this thing in a box here, okay, so that you will remember this guys, that d omega by dt I am going to represent with the what guys, alpha, which is what guys, which is rate of change of what, angular velocity, which is known as what guys, angular acceleration. So we will call this as a what guys, angular acceleration. This is a new parameter that we are introducing here, okay, which is very similar to like what guys, the normal acceleration, okay. So guys, what I can write now, dv by dt is equal to alpha cross r plus omega, and dr by dt is what is v, okay. So guys, if you see here, this is your the total acceleration, okay, that is what, alpha cross r, which is going to be guys what, your a tangential, okay, plus guys omega cross v, which is going to be what guys, your a centripetal. So how I am saying this thing guys, let's see. This we have already derived guys, that its direction is going to come towards the center. Let's see that guys, its direction will be what, in which direction, okay, this acceleration part which is coming here, what would be the direction of this case. So if you see guys, if 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 here guys, if you see, if your omega is increasing, if your omega is increasing, it means what guys, it means the uh, alpha should be what guys, alpha should be in the direction of what, omega only. So guys, if you see here, here in this case, because omega is in the upward direction, and let's say if omega is increasing, in that case guys, what, alpha will be also what guys, alpha will be also in this direction only, okay, alpha will be also what guys, in this direction only. So we can say alpha will be what guys, in the upward direction. Now if you see guys, so alpha is in the upward direction, alpha is in upward direction, and r r is like this guys, okay, r is in this direction. So guys, alpha in upward direction and r is in this direction. So guys, if you do the alpha cross r, you can see that its direction is coming what guys, like this, which is what, which is tangent to this. If you see guys here, if I take, this is alpha direction upward, and this is what guys, r direction. So if you do the what, the cross, alpha cross r guys, it will come in which direction, in this direction, okay. I hope you are getting my point, okay. So if you can do alpha cross r guys, you will get the direction of what, this. So suppose if you take here, this is alpha and this is what guys, r vector, then what we can say, alpha cross r will come what guys, in this direction, which is what guys, which if you can see is coming along the tangent to the curve. It means guys what, this is nothing but guys what, it is your a tangential, it is nothing but guys what, your a tangential. So guys, here I have developed a general relationship for alpha, for a tangential and for a centripetal. So guys, a net is equal to your a tangential plus a centripetal, which is equal to what is, alpha cross r plus omega cross v, okay. So guys, you can remember these two relationships, which are very important in circular motion, and they are most general situation formulas, okay guys. So you should keep these in your mind, okay. So a tangential is what guys, alpha cross r, and a centripetal is what guys, omega cross v, okay. These are vector forms, okay. And guys, alpha is your what, angular acceleration, okay. Alpha is what guys, your angular acceleration. So guys, this is the most general relationship that we can have, okay. Now guys, for normal calculation purpose, because guys, you know that alpha and r is going to be perpendicular to each other, okay. So guys, for general calculation purposes, okay, just for calculation, okay, remember guys, direction now you know already. So guys, a tangential you can calculate as what, r into alpha. Just for magnitude purpose guys, okay, direction you can calculate manually, okay. And guys, a centripetal will be what guys, omega into v, or omega square r, or v square by r, okay. Those already we have discussed, okay. that is what guys, A centripetal now, okay, and that is what guys, A tangential now. So now if you see guys that dv by dt here, dv by dt is not only guys what, omega cross v, it is coming with what, omega cross v, along with that it is having one extra term now. So guys, this is the most general equation of what, the rate of change of velocity, the rate of change of velocity. In the case of uniform circular motion guys, this component was 0, that's why it was not coming there. But now guys, because we are dealing with the what, accelerated circular motion, which is a general situation, so that guys, that's why it is now appearing in the equation. It is now appearing in the equation, okay. So I hope guys till now everything is settled. Now for accelerated circular motion guys, there is a special case that we should know. So guys, there is there is uniform accelerated circular motion guys, uniform accelerated circular motion. So guys, for uniform accelerated circular motion, this is a special case of what guys, the accelerated circular motion. So how we have defined guys this? So if you see, let me write down the definition of this case. When the when the A tangential, of course the magnitude base, okay, when the A tangential is constant of the particle or alpha, guys, here I am just writing what, the vector quantity, not the like what, the magnitude only, okay, because the direction is going to be constant guys for throughout the motion. So when the A tangential is constant of the particle or alpha is constant, then the motion getting performed by the particle will be will be treated as uniform uniform accelerated circular motion. So guys, here if you see, there are few things that we are going to discuss, okay. So guys, here if you see, how do we analyze this motion, okay, how do we analyze this motion, that is very important, okay. So guys, if you see here, this is very important guys, so please pay attention. So guys, if you see here, the velocity and the acceleration both are in the same direction, and they are always guys what, they are always changing as the path is getting changed continuously, okay, they are changing as the path is getting changed continuously. It means guys, it is something look like what, that the particle is moving on a what, straight line, something like this only, okay. And here what, velocity and acceleration is always what, in the same direction, like either velocity and acceleration will be in the same direction or opposite direction. But guys, if you see, they are always going to be what, always going to be along the path, okay, they are going to be what, along the path, okay, along the path. Are you getting me point or not? So here guys, what we can do, we can simply use these formulas very easily. That is what, v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. Just keep this thing in mind, just keep the the just keep these things in mind. What guys, what, that here s will not be displacement, it is going to be distance, it is going to be distance for you, okay. U or v is going to be speed, speed, okay. okay, and A is not A total, it is only A tangential. Okay, so guys, if now I'm telling you the approach, guys, if V and A are in same direction, then you can use these formulas as it is. Okay, and if V and A are in opposite direction, then take either anti-clockwise positive or clockwise and put the sign accordingly. Put the sign accordingly. When I will take some illustrations, guys, it will become more and more clearer. Okay, this is something that I wanted to discuss, guys. Suppose here in this case, let's say if this is the direction that we have taken as what, positive. So if let's say V is in this, the particle is moving in the anti-clockwise direction, we will take it positive. And let's say, guys, the A tangential is acting in this direction, so I will we will take A tangential as a what is negative. Okay, and then guys we can put the values here as per the sign. Okay, and then we will solve this problem. Okay, so this is the normal way of kinematics that we have learned in the rectilinear motion. We can apply this here easily and we can solve the problem also. Okay, but guys, this is not very advisable. Sometime yes, it would be helpful, but not advisable in general. Okay, what we have to do now, we have to move towards what, guys, finding the equations which are more in terms of what, guys, in the angular forms. Okay, which are more in the angular forms, like what, guys, like the angular displacement, angular velocity, angular acceleration, all those things. Okay, so guys, here let me derive some general relationships. Okay, so guys, if you see here if you see that omega is equal to what, guys, d theta by dt. Okay, and alpha is equal to d omega by dt. Okay, and guys, we can use also one more form. Okay, that is what, guys, that is, we know that alpha is equal to d omega by dt. So what we can do here, guys, we can uh, convert this equation in a scalar form for a moment, guys. Later you will get to know that how we have to deal, because direction wise the things we can know that either it will be upward or it will be downward if we are talking in terms of plane. So alpha is equal to what, guys, d omega by dt. I'm just writing signs we will take automatically as per the question, guys. So what we can do, we can multiply d theta here and d theta here and dt here, guys. Okay, so we can do that thing, and then we can write alpha is equal to what, guys, it is equal to d theta by dt is what, guys, omega. So this into d omega by d theta. Okay, so guys, this is scalar form, remember, guys. Okay, this is not a vector form, it is scalar form. Okay, scalar form, remember, guys, this is not a vector form. Okay, because doing this thing in a vector form would be more like chaotic. Okay, because putting the d theta here, if you see, putting the d theta here is not advisable. Okay, I hope you're getting my point, what I'm trying to say. So guys, alpha is equal to what, omega into d omega by d theta. Anyway, also, like, it is going to be a dot product, so that's why, guys, it comes at the end as a what, scalar form only. Okay, so for right now, guys, you take it as what, at a scalar form, and these two are as a what, guys, vector forms. Okay, these two are what, as a vector form. So now, guys, I can derive, there are some general relationships. Okay, so what are those relationships, guys? Suppose if alpha is constant and initial position of the particle from reference line is theta naught at t equal to 0, and its angular velocity is omega naught, okay, at t equal to 0. then 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 what guys, then let's see. Then in that case guys, what we can write like this, that alpha is equal to d omega by dt. So guys, here what we can write, because guys, okay, let me write down like this way, okay, because we can deal with this. Okay, so d omega is equal to what guys, is equal to alpha dt. Okay, now we can integrate this. So guys, here it will be what, your initial omega naught, and let's say later it is what, omega naught vector, and this is what, 0, and this is what guys, t. We have integrated this. So we got guys what, omega naught vector, sorry, omega vector minus omega naught vector is equal to alpha vector into what guys, t minus 0. So guys, what we got, omega vector is equal to what, omega naught plus alpha into t. Okay guys, so this is a vector form that we have derived, but guys, it is not needed as much. Okay, just you remember that if sine of alpha is in, if alpha is also guys acting in the same direction of omega, then guys, of course it is going to increase. If it is opposite direction, it is going to decrease. Okay, so that is very normal thing, but of course we have derived in a vector form also. Now guys, let's talk about the second case, that is what, that is, this is the first equation guys, true for uniform accelerated circular motion. Okay, now guys, coming to the second case, that is what, that omega is equal to what guys, d theta by dt. Okay, d theta by dt. So guys, here if you see, the d theta is equal to what, omega dt. Now the problem is guys, if we integrate this, okay, if we integrate this, try to understand guys, when we will integrate this, we will integrate this guys, this will not be a vector quantity. Okay, these angular positions will not be a vector quantity, so we can eliminate guys these theta and omega. Why? Because theta and omega will be always in the same directions, you know that. Okay, theta and omega is always going to be guys what, in the same direction. So what we can do, we can eliminate these two direction components which are right now on the top. Okay, because otherwise it will confuse you. Okay, it will confuse you. Or okay, let me go like this way. I'll let you know that how you have to use this equations. Okay, so let me integrate this case. Okay, let me integrate this. So guys, let's say uh, this is the integration that we are going to run. So let's say guys, this is initial position theta naught, and this is what, theta. This will be what guys, d theta. Okay, if you will put as a vector, then you will get confused. That's why I was saying. Okay, but okay, let it be like this way only guys. And here omega I can replace with the what guys, omega naught plus alpha into t dt. Okay, now guys, if you see, if I integrate this, try to understand guys. So this will come as a vector quantity, but this will not come as a vector quantity now, because here if I integrate, this part will be what guys, vector, this part will be what, vector. So try to understand guys, that's why here these vector quantities we have to now remove. Okay, we have to remove these, because for a certain time interval guys, this equation can't be applied. Okay, like these direction things we can't use. Okay, I hope you're getting my point what I'm trying to say. So guys, we have to eliminate these directions thing, what, when we are talking about a definite time interval. Okay, I hope you're getting my point what I'm trying to say, because this we have discussed in the start only, that for a definite time interval, the delta theta couldn't be a vector quantity. So guys, in this case, what we can say like this, that theta, guys try to understand, theta minus theta naught is going to be what, omega naught t plus half alpha t square. Okay, I hope you're getting my point. So theta is equal to what, guys, theta naught plus omega naught t plus half alpha t square. Here, guys, of course, alpha is going to have certain direction, either in the same direction of what, omega naught, either in the same direction of omega naught or in the opposite directions, guys. So we have to take care of those things. Okay, so please remember all those things, guys. And if if guys, if theta naught is equal to 0, then we can say, guys, the final angular position will be directly what, omega naught t plus half alpha t square, which is very similar to what, guys, the formula s is equal to what, ut plus half a t square. Okay, so I hope you're getting my point, what I'm trying to say till now. And now, guys, the third equation, that is what, that is alpha is equal to omega d omega by d theta. Okay, alpha omega d omega by d theta. So, guys, if I integrate this, okay, if I integrate this, what I will get, if you see, I can write this as omega d omega is equal to alpha d theta. If I integrate this, guys, okay, remember, guys, the directions we have to take care of these omega alphas manually. Okay, we have to take care of all those things. These equations can't be written, guys, what, in the vector form directly. I think only this single equation we can write in the vector form, but, guys, these equations wouldn't be the right way to write like this way. Why? Because guys, you know that the delta theta is not a vector quantity. So that's why, guys, I'm not writing them in a what, vector form. And wherever the directions are needed, I am going to take care of them, what, guys, manually. Okay, I'm going to take care of them with what, guys, manually. I hope you're getting my point, what I'm trying to convey here, guys. So omega d omega is equal to what, guys, alpha d theta. Now, guys, put the limits. So omega not initial, guys, later is what, omega, and, guys, this is what, initial is theta naught, later is what, is theta, let's say. So, guys, it will become what, it will become omega square by 2 minus omega naught square by 2. Okay, and this will be what, guys, alpha theta minus theta naught. Okay, so, guys, what we can say, omega square is equal to omega naught square, sorry, plus 2 alpha theta minus theta naught, guys. This is the third equation, which is very similar to, guys, what, v square is equal to u square plus 2as. And here, guys, if, of course, theta naught is equal to 0, in that case, then omega square is equal to what, guys, omega naught square plus 2 alpha theta. Okay, so that is what, guys, the special case of this equation. Okay, now, guys, these are the three questions with which we can handle the whole uniform accelerated circular motion. Okay, we can handle the, guys, what, uniform accelerated circular motion. And, guys, now there is one more different type of kinematics problem may come in front of us. That is what, guys, non-uniform accelerated circular motion. Okay, non-uniform accelerated circular motion. And that is, guys, how we can deal, as we have dealt with what, in the kinematics case, we have three differential equations. Those three differential equations is good enough to solve every problem, guys. What are those differential equations, guys? The first one that we are going to use is what, guys, omega is equal to what, sorry, yes, we can use this d theta by dt. But, guys, advisable is what, omega is equal to d theta by dt. This we are going to use, not this. Okay, but because, guys, there is some vector issue that I have told you in the beginning only. Okay, and, guys, if we use what, the second equation, guys, this is the first fundamental equation, guys. Second equation is what, that alpha is equal to what, guys, d omega by dt. This you can use as a vector also, guys, but we are going to use this as a what, guys, like this only. And how to use, we will see in the like when we will start discussing the illustration in the next lecture. You will get to know that how we have to use this. And the third one is what, guys? Of course, that is what, scalar form only. That is what, guys? Alpha is equal to omega d omega by d theta. Okay, alpha is equal to what, guys? Omega into d omega by d theta. That is what, guys? The third equation. So guys, with this we have understood the case what, the kinematics part of the circular motion. If it is a uniform circular motion, it is a accelerated circular motion. And in the accelerated circular motion, guys, if it is a uniform accelerated circular motion or a non-uniform accelerated circular motion. So guys, these things we have covered. Now the theory wise, we have understood the all the ideas. There is one small idea, guys, that is, if particle is not moving on a circular path, if it is moving on a general curve, then in that case how do we calculate the angular velocity? That is one small concept is remaining in terms of kinematics. Okay, so if I'll cover that part of the theory, then after that we'll be done with the theory. Okay, so let me cover that part of the theory in this video only, so that in the next lecture we can just focus on what is the problems. Okay, I'll be taking the like a big lecture on the problems only, so that we can see a variety of problems in the next class. Okay, so let me cover, guys, the next part. That is what, that is, guys, calculation of angular velocity of a particle, of a particle with respect to a point, with respect to a point, to a point, basically, guys, your frame of reference. Okay, frame of reference, when particle is moving on some general curve. Okay, on some general curve. It's a small topic, guys, but it's very very important. So let me cover this here only, guys, so that in the next lecture we will just focus on what, the problems. Okay, so guys, let me add few more pages. Okay, okay, guys, so please listen this, guys, very very carefully, because this is very very important. Okay, this is very very important. Many teachers, guys, they discuss this thing in the very start only. Okay, but I discuss in the end of the kinematics part. Why? Because I feel that when I discuss this in the end, before this, guys, already I have built a certain level of foundation of what, of the idea of angular velocity for a circular motion. So I think it would be much more approachable now to understand the angular velocity in this context. Okay, so guys, let's see. Suppose, guys, see, suppose, let me make a axis here, guys. Okay, and suppose, guys, let's say, guys, this is a some sort of a general curve. We don't know, it is maybe a parabola, it could be a part of what, ellipse, something. Okay, it could be a circle also, we don't know, but I have drawn this, guys. Now if you see, guys, this particle that was moving here, see, guys, so 1 minute, guys, 1 minute. Let's say, guys, right now the right now, guys, the particle is having 1 minute. 1 minute, guys. Mm, let me use like some other way. Okay, I think that would be much better to understand. Let's say, guys, this is the path on which the particle is moving. Okay, this is the path on which the particle is moving. I think that would be much more clarity it will give you. Okay, so guys, if you see, I think those looks parallel only. Yes, now is, suppose a particle which is, guys, here is moving on this path. Okay, it is moving on this path. Okay, there is a particle P. I think this looks straight line. Yeah, I don't think so, guys. Just a minute. Okay, I feel it doesn't look like a straight line. Let me make like this way, not parallel. Okay, now it looks parallel to me. Okay. Okay, so guys, let me choose some different color. Try to understand, guys, this part very very carefully, because this is one of the fundamental way to explain that what is angular velocity. Okay, so guys, suppose this particle is moving on a path like this. Okay, it is moving on a path like this. So guys, if you see right now this is the position vector of the particle. And guys, suppose when the particle reached here, of course guys, it has it has suppose guys, it is moving with the constant speed only. Okay, so guys, of course, if you see, it has covered some angle with respect to what, with respect to this point. Okay, some angle has been what, guys, it has covered. If you see, with respect to what, with respect to this point. Are you getting my point or not? It is moving something like this, guys. If you, when it will go here, this will be what, guys, this will be the angle. When it will go here, this will be the angle. Okay, so it is covering some angle. So guys, what we can say, that yes, this particle is having some angular velocity in this direction. Okay, so how do we calculate this angular velocity? This is a very general thing, guys. So try to understand, guys, this very very uh, uh, this is very very important. Okay, so guys, please pay attention. Guys, you know that angular velocity is defined for an instant. It is defined for an instant, guys. Means, guys, it is not defined for a general interval. Okay, it is defined for a very small time. Means at an instant it is defined. Okay, try to understand this thing. So guys, here if you see, mm, let me choose some color, guys, here, a little brighter side. Yes, I think that will work. So guys, if you see, there are, guys, if you see, there are two components of, let's say, guys, this angle is what, is alpha. This angle is what, guys, alpha. So guys, there is two component of this velocity, that is what, one is this. Okay, and one is what, guys, this. Okay, one is this and one is what, guys, this. Okay, so if you see, guys, this is your position vector, this is your position vector. Of course, guys, this thing, this velocity component, okay, which we can say as v cos alpha, and this is what, guys, v sin alpha. If you see, guys, this v cos alpha is the component which is going to elongate, or which is going to increase this r. Okay, the magnitude of r is going to change because of v cos alpha. Are you getting my point or not? V cos alpha is going to increase the length of the r. Okay, v cos alpha is going to, guys, what, increase the length of the r. So it is not going to change the direction of r, but it is going to change the, guys, what, increase the magnitude of r. Okay, and guys, if you see here, this v sin alpha, sorry guys, this v sin alpha, if you see, this is, guys, what, perpendicular to r. This is what, guys, perpendicular to r at this moment. So guys, of course, this if it is perpendicular to r, it can't change the magnitude of r. It can't change the, guys, what, magnitude of r. But guys, because it is perpendicular, it can rotate the r. It can rotate the r. It's like, guys, what, if it is a rod, and you are holding a thread which is attached to this rod, guys, and you are holding this thread and pulling it with certain velocity, it is going to rotate. I hope you're getting my point. Okay, and this rotation is, guys, what, going to change the direction of r, guys. Okay, and you are going to have some angular velocity. So guys, of course, here if you see, this v sin alpha is the component of the velocity which is the causing agent, due to which, guys, it is what, it is rotating. It is rotating. I hope you're getting my point. So guys, here if you see, this is your component, which is what we can say as v perpendicular. Okay, v perpendicular component, guys. Okay, so this is the component, guys, which is going to rotate the particle. Okay, which is going to give certain angular velocity with respect to what, guys? With respect to a point or a frame of reference. Okay, I hope you're getting my point. Okay, so how do we define, guys, the angular velocity? So if you remember, guys, you remember, so I have written that this v vector would be equal to what, guys? Omega cross r, where this should be what, guys? This should be your the velocity, which is the component which is what, guys? Making the particle to what, to rotate. Okay, so of course, guys, because the particle is having certain angle of what, rotation, you can say. Okay, rotation, I think it's not a correct term, but guys, it has a certain angle of what, movement, certain angular movement that it is having is because of this component, not because of this component, guys. So we can say that v perpendicular component is equal to what, guys? Omega cross r. So for calculating the magnitude, guys, just for calculating the magnitude, we can say, for calculating the magnitude, omega is equal to v perpendicular divided by what, guys? R. Okay, this is not for direction, guys, it is just for what, for the magnitude calculation. Okay, direction we can find out manually. For direction, guys, this relationship is quite like uh, quietly it will give us what, guys? Direction, if it is needed. Okay, if it is needed, this is the important relationship, guys, that we have to keep in mind to find out the angular velocity in a general situation when the particle is moving on a what, guys? On a general curve. Okay, when a particle is moving on a what, guys? General curve. I hope, guys, till now everything is settled for you. Everything is what, guys? Settled for you. So now, guys, we are equipped with the concepts, we are equipped with the what, guys? The relations that we should need. Now we can take some good illustrations in the next class, and guys, after that, in that only I'll discuss about the idea of what, guys? The relative angular velocity also, when we will when I will be taking the illustrations. At that point of time, guys, only I will take this what, the relative angular velocity as a concept also, that what is relative angular velocity in the case of what, is angular velocity. Because relative velocity we have discussed in the kinematics, but how the angular relative angular velocity has been defined in the case of circular motion. Okay, or in terms of angular variables, how it has been defined, we will discuss during the illustrations that I am going to take in the next lecture.